we start again. So here you can see just to observe that what we have said is that in two conditions that you see that particularly at field capacity the soil would be perfectly friendly for vegetative growth, and not necessarily certainly at soil wilting point when there is the plant would be almost, the plant would not find any water as such to get, so that it can generate its food, and it can have a balance in its structure itself. So that is called the soil wilting point, when the soil that particular condition would make the plants to die if it continues to remain in that situation for long. Particularly the small plants die. Larger plants, by virtue of their entry to a lower depth of the soil, they can still survive. But you find that if soil wilting point, particularly in a drought situation, in a situation of drought, you find that the soil has reached its wilting point, and where wilting point means wilting point for the plants, where the plants can no longer sustain, no longer remain in that. Another important place is when the soil is completely saturated. Particularly the soil saturation is observed like this. Say if you are seeing the heavy shower on the soil, you will find after some time the water is beginning to gather on top of the soil. Okay, beginning to gather on top of the soil. So what has happened is soil has already saturated with water. Only then the water has been left out. Only then the water has gone out of it. So in such situation, if this is remaining continuously for quite some time in the soil itself, the soil would be finally would be breathless, would not find any air for it to sustain, for it to live. So, and due to lack of air in the soil itself, the plant roots, they would begin to wither away, begin to die, will begin to dry down, begin to completely dry down, because there would not be any air available for its respiration. Remember this. The root respiration is a very important part of the soil of the plant. Anyway, so here this is what has to be observed about. This is what has to be observed about the soil water, and this is what it makes a difference. So whatever in a particularly in an engineering decision, if you are making, if you are working as an environmental specialist, you should try to put the soil in the field capacity. You should try to work out, see that the soil comes back to its, or soil is maintained the soil water is maintained at field capacity. So the soil texture, next comes is soil texture. This is the soil texture. Also a very important part of the soil, not very critically important, but on the other hand it has a great role to play. As I was discussing you yesterday, as well as in the lab class, and also in the last class that we discussed, the soil texture also has a great role to play. It's nothing but soil texture is the granulometric distribution of particles in the soil. Granulometric distribution of particles in the soil. So this is about just to say about how the soil, the soil is distributed. So before we go into that, what are the particles or the different size of particles that we generally find out in soil? Say this is what is essentially the soil consists of. This is gravel, very coarse sand, medium sand, medium sand, fine sand, silt, clay. Okay. So there are two systems actually by which it can be classified. This is the texture classification. So you can see this is the classified, this is texture classification. Texture classification. This is is basically a British system or internationally accepted system. And another just goes as US Department of Agriculture system. US Department of Agriculture, they generally explain it differently. So both the cases, it is above if it is in case of dia, this is also dia. Above 2 mm is basically gravel. So above 2 mm is gravel. Gravels actually except for supporting the plant structure, they don't contribute much. So this is whether only purpose that it serves is mostly to provide a structure for the plant. Very coarse sand, there is this distinction is not essentially available in the international system. This is 1 to 1.0 to 2 is the very coarse sand, whereas this coarse sand is 0.2 to 2.0. This is 0.5 to 1. This is medium sand, is not existent, and this is 0.1 to 0.5. Right. Fine sand is 0.02 to 0.2. This one is 0.05 to 0.1. Silt is 0.002 to 0.02, less than 0. So it's less than 0.02, less than 0.02 is clay. So here it is also the same, only thing is 0.002 to 0.05, and this is also anything, the last one is 0.02. this is same, only they made a subdivision. So you can say in the international system there is nothing like coarse sand or medium sand like this. It is only sand. They have made a distinction as to coarse, very coarse sand is only told as sand here. Fine sand is there is a distinction of fine sand. Silt is given here 0.02 to 0.2, 0.002 to 0.02 is silt. Clay is anything less than 0.002, and in both the cases this remains the same. Now having to say this, there is a nomograph, that is USDA nomograph, that generally provides a textural classification. I will not go into in most of all books of environmental engineering where the soil is dealt, and in agricultural engineering wherever it is dealt, you will find that the soil nomogram. This is soil nomogram. It says just soil nomogram, which is basic characteristics is this is basically a triangle. Just I'll not. This is percent clay, percent sand, and percent silt. Percent silt. This one is the direction is like this. This is like this, and this one is like this. So you can see this. So for say if we have identified that sand, silt and clay, the sand, silt and clay. So in such cases the sand, silt and clay, that mostly the fines percent, the sand would be included. The sand is the sand plus say fine sand, now here the distinction is this. Remember this, sand would mean anything between 2 to 0.5. Please, other than what has given to you, please take this. This is what is also very important, particularly to use this nomograph. This is 0.05 to 0.002 mm and clay. Clay remains the same, that is 0.002 mm. So what you do is, you just suppose any kind of sand, after you have found out the values of sand, silt and clay. Suppose you have find sand, silt, clay, okay, the sand, silt and clay as x, y and z. So you would plot this along, say along the x here, say sand here along this direction, along increased direction you find x here. You find percent sand is this, you find say clay to be somewhere here, and silt to be somewhere like this, silt to be somewhat like this. So if you just plot it like this, right, so you would parallel to this line. If you just can draw it like this, is parallel to this line, wherever almost closely wherever they meet, this would give you the particular classification of the soil. This is give you the particular classification of the soil. For example, if soil is 40% sand, silt and clay, if it is say composed of 40% sand, 40% silt and 20% clay, this would be known as loam. Similarly, if it is 60%, 30% and 10%, it would be known as sandy loam. Soil with 60%, if the soil is 60% or more clay, say where it is 60% or say 65%, more than 60%, say this one is 10% and say this one is 25%, like this. Okay, you find this one would be just be known as clay. Just be known as clay. This is a textural classification. This would just be known as, the texture wise it would be known as loam, sandy loam, clay, like this. Okay, so this is what is the soil texture. So you would be using this, you need to use this classification of the soil what you have to remember is, you draw a line parallel to this line here, you draw a line parallel to this line here, and then wherever these three lines meet, wherever three lines quite closely meet in a particular region that they show, it would not necessarily meet at one point. The region that it shows is essentially the region it would near about show would be the region of its texture classification. Okay.
So what is the scale on that lines?
The scale is, the percent clay. Say this percent clay is percentage. It is percentage. So
by
total
weight
is 100%. Total by weight. By weight. Essentially by weight. Yes. Always by weight. Because this is being a solid substance, so it would be always by weight. Okay. So you can write by weight. By weight as well. So here this is what is called the soil texture. But more important than this soil texture is the soil structure. More important than this is soil structure. Here is the most important part, the soil structure. If you just so structure can be called as structure can be called as texture plus the agglomerating substances and agglomeration substances and the process of agglomeration This is process of agglomeration is important, should be identified together. They should be identified together. The process of agglomeration should be identified together. Why? What is generally observed, this is what is that this would generally mean structure, inclusive of texture. What is agglomerating to that? See, if there are loosened particles, when you this is soil as we have done in the texture measurement of texture, different granulometric distribution, these are particles separate, that is how we consider. But if you just observe the particles being together in an agglomerated state, that is what is the texture of the soil. So this is the texture, this is the structure of the soil. The structure of the soil that we'll be finding the structure of the soil. This is mostly, this is so here the different kinds of this agglomerating substances we have discussed about that sand, silt and clay. The most of these particles, we'll come back to that, what are the particles all about. But these agglomerating substances are of great importance. These agglomerating substances, agglomerating substances are mostly liquefied organic and inorganic plus organic substances they have another important property. They have an agglomerating property. Agglomerating property existing So most of these agglomerating properties, they would also has agglomeration. Apart from agglomeration properties, they would have, say, they would also provide a different types of structure just because of property, right? Okay. Agglomerating property existing, and secondly, this various kinds of substances working together as soil epoxy. Soil epoxy, the epoxy is the agglomeration or the gum that it works with. So all this loosened, when loosened, they are texture. When they are agglomerated together, they are structure. So what happens is, in the case of disturbance of the soil, suppose if you are picking the soil, if you are shoveling the soil, like in such cases, what happens is, these agglomerating substances are very sensitive substances. They are remaining in an inorganic matrix, very closely held together, right? Now, as soon as these are highly prone to oxidation as well, they are highly prone to oxidation, and whenever they are oxidizing, they are becoming soluble. So what happens is, if you are disturbing the soil, these substances begin to oxidize themselves first, and then when they are oxidizing themselves, they are coming out of the matrix as a substance which is readily soluble in water. Now as soon as the rain falls on top of that, with the rain they become soluble and go out of the soil. This does not take place in the most of the soil surfaces, undisturbed soil surfaces, largely because the water can percolate in the soil, but the material in the soil is not oxidized. The material itself in the soil is not destructured. So the agglomeration property remains intact under undisturbed condition, but in disturbed condition, these agglomerating properties begin to go away. The agglomerating substances begin to get oxidized and become perfectly soluble to water under normal temperature pressure, under STP, and so they go out of the soil. So the soil gets out of its structure. So these are the structure, the most important structures that we generally talk of. Let me give you some idea about the structures. So this is how the structures look like. This is called a granular structure. Right? The next one is the prismatic structure. You see here it looks like a prism. So you can see this is prismatic structure. Okay, whereas where the granules are not generally observed, I mean it looks like as if it is almost a rock. The grains are not generally very clearly visible. Is that the soil, the grains cannot be identified. This is particularly This is what is known as the massive structure. Massive structure. So here, some properties that we can very well write out, that here is this permeability. If you just try to observe this permeability, then is permeability and comments. Say the other usual comments, the comments, this permeability and comments. You can see this, this is highly permeable, high rapid permeability. They call it a rapid or high, as you can write, but generally high in organic matter. High in organic matter. The prismatic soil is the permeability is moderate. The permeability is moderate, and average organic matter, I mean almost usually existent, average organic matter. And if you just see massive is very slow, so it's a very low or slow, as you can say, low permeability. This is more of a field type. The characterization, rapid, slow is this, as you can see the massive becoming slow. So here, and this particularly in the massive and unstructured unweathered clay. This is unweathered clay. If this unweathered clay, this would look like this. Unweathered clay would look like this. Unit size, if you can write out this one, generally in agriculture, there are so many, still they use a lot of APS system, yet inch, pound are all very much still in use. But just say, just for your purpose here, up to 6 inch in diameter. And this one is up to 6 inches, is unlimited. Unlimited means, steel would be not unlimited, as within the soil. Within the soil, mostly the gravel would be less. So, say unlimited, maybe say particularly say 2 mm that we have discussed. So this is what is the typical structures that we generally observe in the soil. There are few more. This is few more, which is the blocky one. The blocky is nothing, is of small, larger particles like relatively larger than the granular size, up to about, say, as you can see, compared to granular, permeability should be high. Permeability moderate. Unit size would be about, say, 4 inch up to 4-inch diameter, up to 4-inch diameter. And this is what is, the other things are like the comments that can be made. The comments that can be made is, it is a process. The comment you can write is degenerated condition of massive soil. Sometimes this can be another kind of soil that we generally see, which looks like a plate, which is looking like a plate like this, in a platey soil. Particularly in the river basins, you will find this kind of soil. Okay, so this is called platey. This is, as I have said, blocky. This one is platey. You can see permeability should be low. Permeability is mostly, this vegetative is very slow permeability. That unit size is inconsequential. It doesn't matter because it looks like plain. Is occurrence, comment. River basin soil, say, so this virgin surface soil. So you can find them in the virgin surface soil. So this is what is the platey structure of the soil. So you can find that the soils can come in different structures, and this structure is all important about soil. It's extremely important. If the soil structure is maintained, and remember one thing, to bring back to the soil structure is extremely difficult. Once it is destructed, you can think of, say, once this is destructed, all these things are destructed. Generally what happens in an engineering construction, dam construction, road construction, building construction, wherever, in a mining activity, is when you are disturbing this, completely destroying this, to bring it back to a certain structure is extremely difficult. And that is what remains the most important activity of soil reclamation, to bring it back to a certain structure, so that the structure is all important, because the structure is which would help them to keep the nutrients within the soil, would help them to keep the soil water in them, would also help the soil to hold on to the plants, so that the plants do not fall off. The plants can stand on its own. So this structure remains the most important part of soil. If the structure is destroyed, much of the soil is destroyed. So having said this, this is another important thing that we discuss, is just a few minutes on this, the soil organic matter. The soil organic matter that we see is soil organic matter also has a lot of things to discuss. The soil organic matter, the basic purpose of the soil organic matter. This is particularly composed of animal excreta, fallen leaves, then there's particularly the remains, animal and plants remain, plant remains, animal and plant remains contribute to the soil organic matter, soil organic matter. So soil organic matter. The soil organic matter, the purpose, this, we will come back to this characteristic of the soil organic matter. We'll come back to the purpose of the soil organic matter, but before that, let me explain, what are the important effects, why this soil organic matter is extremely important. Soil organic matter importance. If you think of the importance, this fresh organic matter reduces the impact of falling raindrops. Impact of falling raindrops. Falling raindrops, if this impact, if it is not reduced, it will force the soil to plastic deformation. It would allow the soil to force the plastic deformation, as a result of which the soil would be destabilized, the soil would be disengaged from the parent body. The soil would be disengaged from the parent body. So reduces soil erosion. So from the first, you can see, from the first point, we can derive this, that the second point. The third one is maintains soil temperature. Soil temperature, as we have said, I have said, the soil temperature becomes extremely important. Maintaining soil temperature, in many cases, the difference from the outside temperature to the soil temperature, say soil temperature at a depth of 250 centimeter, soil temperature at a depth of 250 will be about 5 to 7 degrees centigrade lesser than that in the atmosphere. And this one is particularly very critical. It becomes particularly very critical, 5 to 7 degree less from the surface temperature. Think of this. So in a hot summer, when the temperature outside would be 45 degrees centigrade, you have the soil, the plant roots are finding all the substances at a temperature of, say, 40 degrees centigrade. That makes a lot of difference. That makes a great number of differences. It also, this serves as food for animals like insects, worms, and rodents. So you can say the start of the food chain. The start of the food chain. The start of the food chain is of great role, great importance. This is where it starts the food chain. There is the fifth point is say this also decomposed organic matter. Decomposed organic matter helps forming carbonic acid, there is CO2 plus H2O, carbonic acid, the carbonic acid releases, carbonic acid helps in releasing metallic and non-metallic nutrients. Decomposed organic matter helps forming carbonic acid. The carbonic acid helps in releasing metallic and non-metallic nutrients. That is, carbonic acid forming, in the reactions that many of those substances would be ionized. Many of these substances, say the substances that we require, the phosphorus, boron, calcium, magnesium, iron, phosphorus, all these that are required, generally being released in the soil environment by the carbonic acid, with the help of this carbonic acid. So it says metallic nutrients for the plant uptake. The sixth point is the decomposed organic matter produces slimes and gums. This is what form the epoxies, the soil epoxies, or the soil epoxies or the agglomerating substances. This is what leads to the soil structure. This helps in maintaining the soil structure or evolving a soil structure also, by which the soil structure would be evolved. So maintaining an evolving soil structure. It maintains the soil structure. It also, if the soil is disturbed, suppose the soil is being dumped at one place, the evolution of the structure, the soil evolves. The evolution of the structure is helped by the soil structure also. Evolution of the soil structure is led by the decomposed organic products, organic material. This is the last point here is, the organic matter is this helps in absorbing and holding absorbing and holding water. Helps in absorbing and holding water. And nutrients for plant use. So what is this? Is organic matter. So in engineering aspect, if you say how this soil organic matter gets reduced by soil tillage, increased cultivation, engineering and project disturbances, and so in engineering and project disturbances, and also pollution, say air also reducing due to say increased air pollution. If you remember in the acid rain that we did, acid rain is another important reason why the soil organic matter gets reduced. And this, if this soil organic matter gets reduced, it can be enriched by gap cultivation, then foraging, say foraging by say nitrogenous plants, and also by manuring. Can be enriched gap cultivation, foraging by nitrogenous plants, and manuring, using manuring or fertilizers, organic fertilizers. So you can see this, this is how the soil, this is important characteristics of the soil, how they have a role to play, what great role they play. So all these things get distracted whenever there is a major soil disturbance. Okay, we'll take up this again related to soil again in the next class.